Welcome back to this series on topology. In today's video, we'll be discussing subspaces, which are a way of giving a subset of a topological space its own topology that is compatible with the topology on the larger space. You can find a link to all the other videos in this series by clicking on the info thing that should appear right now. Rather than simply presenting the definition for the subspace topology, I'd like to motivate how one would come up with such a definition. Now, the situation we'll be considering is the following. We suppose that we have some topological space X and some subset of X, which I'll call S. Now, the fact that X is a topological space means that we have a topology on X, which is a collection of open sets. And let's call this collection tau of X. So the topological space X is really this pair consisting of the set X and this collection of open subsets of X. On the other hand, this subset S at the moment is just a set. We don't yet have some collection of open sets on S that make it into a topological space. So our job will be to designate some open sets tau S, which should form a topology on the subset S. So I'll mark a question mark here because we don't yet know what this tau S is going to be. Now, in principle, there are many topologies we could put on the subset S. For example, we could just put the discrete topology on S and declare every subset of S to be open. However, we would like this topology that we're going to define on S to be related to the topology that we already have on X. One place to start is to notice that we have a special function from S to X, namely the inclusion. So I'm going to draw this with this hook arrow, and denote this iota S. So this is the function that maps S into X by just restricting the identity. For example, any point Y in S will just be mapped to the same point Y seen as a point of X. Having this inclusion is really useful. For example, if we have some function going from X to Y called f, then we can compose this function f with the inclusion to get the function f after iota S, and this is just the same thing as restricting f to the subset S. Now, if X, Y, and S aren't just sets, but instead are topological spaces, and for example this f would be a continuous map, then in order to do this restricting business, we would also need iota S to be continuous. That way, if we compose these two continuous functions, this restriction will then again be continuous. Therefore, if we'll want to use these useful features of this inclusion map, we'll want this inclusion map to be a continuous map from S to X. And making this inclusion continuous will restrict the possible choices of topologies tau S we can put on the subset S. Let's think about what this means. So suppose we have some open set U, which is a subset of X. In our picture, perhaps U could look like this. Now, if iota S is to be continuous, then the pre-image of every open set in X under this inclusion map needs to be open in the topology on S. So what we're going to consider is the pre-image under the inclusion of this subset U, and in fact, this is nothing but the intersection of U with S. This follows straight from the definition of pre-image. The pre-image of U under iota S, this is just all the points small s in S such that the inclusion of this point S is within U. But because the inclusion of this point small s is just, well, it's just S in X, this means that we have the pre-image being all the points small s in S such that S lies in U, and this is the same thing as the intersection of U with S. In any case, this means that if the inclusion is to be continuous, then for any open set U in X, the intersection U with S needs to be open in this new topology we're going to be defining. So in our picture, given any such red set U, we're going to have some intersection with S, which is possibly empty, but in this case, this intersection needs to be an open subset of S in the subspace topology. So that's a necessary condition in order to make delta S continuous. So our discussion so far has shown that the following set, namely U intersection S, where U is open in X, this set needs to be a subset of tau S if we want this inclusion to be continuous. We could now ask whether we wanted to include any other subsets of S as open sets in tau S. Here there are really two extremes one could think about. On the one hand, one could think about including as many open sets as possible into tau S, such that this inclusion map is still continuous, or one could try to include as few open sets as possible in order to still have this inclusion be continuous. Now, the solution to the first approach, namely including as many open sets as possible, would just yield the discrete topology. This would mean saying that every subset of S is open, and in particular, this would also mean that this inclusion is continuous because, well, we need the preimage of every open set in X to be open in S, but every subset of S is open, so in that case, any map out of S is continuous. Because we don't necessarily want to end up with a discrete topology, this one extreme is probably the wrong approach, and instead we choose to include as few open sets as possible into tau S. So we know that we at least need to include sets of this form into tau S, and the question is whether we need to include any more in order to make tau S into a topology. Now, as it turns out, if you consider this collection of subsets, namely the intersection with S of all open sets in X, this is already a topology. That means it satisfies those three conditions that we need for a topology, namely that the entire subset is open in the topology, the empty set needs to be open in the topology, then we need that arbitrary unions of open sets are again open, and finally that finite intersections of open sets are again open. So because this collection turns out to be a topology, which is something that one can check, then if we end up setting tau S to be equal to this collection, then because our argument showed that any topology that makes this inclusion continuous needs to include this set, which is tau S, it means that tau S is the smallest topology on the subset S, which makes this inclusion continuous. To briefly recap, we started with some topological space X, which has already some topology tau X on it, and an arbitrary subset S of that space. And then we asked, okay, what do we want the topology to be on S in order for it to be compatible with this pre-existing topology on X? We then identified this inclusion map as being essential to the fact that S is a subset of the space X. And so in particular, we want this inclusion to be continuous, and so we need to choose this new topology tau S accordingly. Now, continuity of this inclusion means that for any open set U in X, the preimage under the inclusion, which happens to be the intersection of U with S, needs to be open in this new topology tau S. This means that this set down here, which is the set of all intersections of open sets in X with S, will be included in any candidate for tau S. So in particular, if we set this collection to be equal to tau S, then our choice of tau S will be the smallest topology on the subset S that still makes this inclusion map here continuous. All of this only works if this collection down here is actually already a topology, which luckily it happens to be. All right, so let's recap by stating the official definition for the subspace topology. So we let X be some topological space and S be an arbitrary subset of that space. Then we define this topology on S, which is called the subspace topology, as follows. It's all the subsets U of S such that U is the intersection of an open set V of X with the subset S. Redrawing our picture from before, if we have the space X here and some subset S here, then the open sets of S are precisely the intersection of open sets U of X with S itself. So that's this shaded area. Conversely, if we pick some subset of S, so maybe this one here, then this subset is open precisely when there is some larger set in X such that this larger set intersects S in this shaded area. Let's now look at some examples. The first example we'll look at is S1, which is the union of the closed interval 0, 1 and the open interval 2, 3, seen as a subset of the real line R. The picture for this is as follows. We have the real line here, then we have 0 somewhere, and now our subset is the closed interval from 0 to 1 and the open interval from 2 to 3. We can now ask whether a given subset of S1 is open in the subspace topology. For example, we could choose a small open interval here, which is maybe the open interval from 1/3 to 2/3. And now we can ask whether this is open or not in the subspace topology. Well, this open interval 1/3 to 2/3 is just the intersection of itself with S1 because it is contained within this closed interval from 0 to 1. Moreover, we know that this subset is open in the larger space R, which by definition means that this subset is open in the subspace topology. This is perhaps unsurprising. We took something that we know is an open set of the real line, and it turns out that it's also an open set as viewed as a subset of the subspace S1. There are, however, some surprising effects that can occur with the subspaces. For example, consider this closed interval from 0 to 1 as a subset of the subspace. We can now ask whether this is open or not. Now, because we have some space around this closed interval, we can actually consider a slightly larger open interval of the real line around it. This orange interval could, for example, be -1/2 to 3/2. And in fact, the closed interval from 0 to 1 is actually the intersection of this slightly larger open interval with S1. This fact should be clear from the picture. Now, because this interval here is open in the real line, then by definition, because we've written 0, 1 as the intersection of an open interval with S1, this means that 0, 1 is actually open in the subspace topology on S1. On the other hand, we know that this is not an open subset of the real line. Hence here we have an example of a subset that is open with respect to the subspace topology, but that is not open in the larger space. Therefore, when we're talking about open or closed sets in a subspace, it's always important to emphasize whether we're considering that subset relative to the subspace or relative to the larger space. This effect becomes even more pronounced in the following example, where we're considering all the points 1 over n, where n runs from 1 to infinity, as a subset of the real line. So the picture for this is that we have the real line here with 0 somewhere, and now we look at points 1, 1/2, 1/3, 1/4, and so on. So these points, they always get closer together, but they never reach 0. And we could now ask, for example, whether the point 1/2 is open in the subspace topology. As before, because we have some space around the point 1/2 and the other points in S2, we can look at a small open interval, which I'll just call I, around this point 1/2. And now we can write 1/2 as the intersection of this interval I with S2. Again, I is open in the real line, so by definition, the point 1/2 is going to be open in the subspace topology on S2. On the other hand, we also know that points are not open in the real line. Now this argument actually works for any point we would pick in the set S2. So in fact, every point in S2 is an open subset of S2, which means that the subspace topology on S2 is actually the discrete topology. In summary, we've seen that the open sets in the subspace topology may not be open sets in the larger space. However, open sets in the larger space do seem to always be open sets in the subspace topology. So here one just has to be careful whether one is talking about a set being open or closed with respect to the subspace topology or with respect to the larger space. Similar comments also go for things like the closure or the interior of sets, because these concepts are defined in terms of open and closed subsets of a space. It means that the closure of some subset is going to be different if one thinks of it being the closure in a subspace or the closure in the larger space. Similarly, if one has some subset of a subspace, then taking its interior in the subspace might be different from taking its interior in the larger space. However, the open sets and closed sets of a subspace aren't entirely unrelated to the open and closed sets of the larger space. And this is something that we'll show in the following proposition. So for this, we suppose that U is some subset of a subset S of a topological space X. Now, part A of the proposition says that if U is open in the larger space X, then U is also open in the subspace S. This is something we saw in the first example we looked at. And similarly, if U is closed in the larger space X, then U is also closed in the subspace. I'll just prove the open part. So consider U sub X an open set. Now, by assumption, U is a subset of S. That's our hypothesis up here. So we can rewrite U as U intersection S. And now because U is open in X, by definition of what it means to be an open set on the subspace topology, this means that U is open in S. Namely, the open sets in the subspace are precisely intersections of open sets of the larger space with S. And this is how we've been able to write U here. So that already concludes the proof for this part A, looking at the open subsets. For our closed subsets, one would just have to take the complement of the closed subset, which is open, then one does the same argument, and then one takes complements again. All right, so if we have an open or a closed subset in the larger space, that subset will again be open or closed in the subspace. However, we've seen already in the examples that the converse of this doesn't hold, so we might have an open subset of the subspace, which is not an open subset of the larger space. However, when the subspace is itself an open set of the larger space, then any open subset of the subspace will also be an open set of the larger space. And conversely, if the subspace is itself a closed subset of the larger space, then any closed subset of the subspace will again be a closed subset in the larger space. Therefore, part B is sort of a partial converse to part A. It's saying that it doesn't always happen that open subsets of a subspace are open to the larger space. This, however, does happen when the subspace is itself an open subset of the larger space. I'm again just going to prove the open part. So suppose that U sub S is open in the subspace topology. So it's open in S. By definition, this means that U is equal to S intersection V for V sub X, an open set in X. However, now S, by assumption, is open in X, and we know that V is also open in X. And so here we've expressed U as an intersection of two open sets of X, which means that U is also open in X, just because finite intersections of open sets are again open. So that proves B for open sets, and the variant with the closed sets follows again by taking complements. To reiterate the take-home message from this proposition, if you have some subset of the larger space, which is either open or closed in the larger space, then the same property will also hold in the subspace. However, the converse only holds under more restrictive circumstances. Next, we turn to an abstract way of characterizing the subspace topology. And this sort of continues our line of thought from the very beginning of the video, where I tried to motivate the definition for the subspace topology. For this, we're going to consider some subspace S of a topological space X with the subspace topology. Now, the claim is that such a subspace S has the following property, namely that for any other space Y and function from Y to S, this function f from Y to S is continuous precisely when its composition with the inclusion of S into X is continuous. It's perhaps easiest to parse this statement by looking at the diagram down here. So the initial data that we have are this topological space X and the subspace S, which automatically comes with this inclusion map yada S. Now we consider some arbitrary topological space Y and a function f going from Y to S. Now the claim is that this function f is a continuous map from Y to S if and only if its composition with the inclusion, so that's doing f and then this inclusion, so if and only if this composition is continuous. The statement might sound a bit complicated, but we'll see in the proof that it's actually pretty straightforward. So for the first direction, suppose that f is a continuous map. We already argued in the motivation that yada S is a continuous map, so because yada S is continuous, this implies that also the composite yada S after f is continuous, because the composition of continuous maps is again continuous. So that already proves this one direction. Conversely, let's suppose that the composite yada S after f is continuous. And now we would like to show that the map f itself is continuous. So for this, we're going to let U be some subset of S which is open. And now we need to check that the preimage of U under F is open in Y. Now, being open in the subspace topology means that U is the intersection of V with S for V being an open subset of X. On the other hand, we saw before that the intersection of some set with S is actually the same thing as the preimage of yada S of that subset. Now we want to check whether the preimage of this subset U under F is again open in Y, so that would be the continuity of F. So we're going to check what F inverse of U is. Well, we know that U is equal to the intersection of V with S, and we know that this is equal to the preimage of V under yada S. On the other hand, if you iterate taking preimages, So if you first take the preimage under yada s and then the preimage under f, this is the same thing as taking a preimage under yada s after f of the set in question. This is something you can immediately check by just writing out the definition for both sets. Now, because we've assumed that this composite yada s after f is continuous, and we know that V is an open subset of X, this means that this preimage here is open in Y, and because of the equality we've established, this means that the preimage of U under F is also going to be open in Y. And by definition, because we've started with an arbitrary open set of S and shown that its preimage under F is open in Y, this means that F is continuous, and this completes the proof. At the moment, this characteristic property might still seem mysterious, so I'll say two things that will hopefully clarify a bit. First, this property actually characterizes the subspace topology. So if you have any other topology on S that satisfies this property, then actually S with this other topology will be homeomorphic to S with the subspace topology. Therefore, this characteristic property is a way of defining the subspace topology up to homeomorphism, but it doesn't mention anywhere an explicit construction of what the open sets of this topology need to be. The second reason for why this property is useful is because it will immediately allow us to prove certain things about restricting continuous functions and then being able to show that these restrictions are again continuous. This is the content of the following corollary. Here we suppose that x, y, and z are topological spaces and that f from x to y is a continuous function. Part A says that if we have a subset S of x, then f restricted to S, so that's the function going from S to y, is again going to be a continuous map. Let's illustrate the situation with a diagram, sort of like the one we had in purple. So we have x, and we have a subset S of x, which means that we have this inclusion map. And now we have a map going from x to y, which is continuous. And here this inclusion I called yada s. And now the claim is that f restricted to S is also going to be continuous. But this follows from the fact that if we compose f with yada s, then this is equal to f restricted to S. And because both yada s and f are continuous, so is their composite, which is just this restriction map we're interested in. So being able to restrict functions in the domain follows from the fact that this inclusion map is continuous. So this is one of the reasons why we wanted this feature of being continuous for this inclusion. Turning to part B of this corollary, it says that if T is a subset of Y and the image of X under F is a subset of T, then the restriction where we view F as a function from X going to T is also going to be continuous. The situation is as follows. We have this function f going from x to y, and we're supposing that this is a continuous map. And now we have a subset T of y and an inclusion yada t, and we want to view f as a function going from x to t. And this only works if the image of the entire set x under f is actually included in T. In order to show that this map f here, viewed as a map from x to t, is continuous, we're going to use the characteristic property of the subspace topology. In this case, we're viewing T as a subspace of y. The characteristic property says that this map is continuous if and only if the composite of it with the inclusion is continuous. But now we observe that the composite of this map here with the inclusion is just equal to the map going from x to y. So maybe here we should differentiate. So I'll call this map here f tilde for the moment. And it's in fact the case that this map f from x to y is equal to yada t after f tilde. This is something you can check by just looking at what these two maps do to elements of X. So if we have some element u in X, then this gets mapped by f tilde to f of u viewed as a element of t, and then the inclusion will map this up to f of u viewed as an element of y, and of course f just maps u to f of u, so these two maps are equal. In any case, we know by assumption that f is continuous, so this map going from x to y, which we've rewritten as this composite iota t after f tilde, and now by this characteristic property, this composite being continuous is equivalent to f tilde being continuous, and so we've shown that f tilde is continuous, and this proves part B of the corollary. Finally, part C of the corollary says that if we have y being a subset of z, then the map, which we get by viewing f as a function from x to z, is also going to be continuous. So we had this map f going from x to y, and now y is a subset of z. So we have this inclusion iota y, and now if we view f as a map going from x to z, so we've extended the codomain, then this map is also continuous, and this again follows because this new f, which maybe is better to call it f tilde, is the composite of f with iota y. So it's iota y after f. Okay, so the point of this corollary is just that defining the subspace topology in the way that we did means that also if you restrict maps in the domain or codomain or extend them in the codomain, that this preserves continuity of the maps in question. Finally, the following proposition summarizes some important properties of the subspace topology. So for this, we let S again be a subspace of a topological space X, considered with the subspace topology. Part A concerns taking iterated subspaces. If we have a subset R of S, then we can either consider R as a subspace of S, or we could think of R as being a subspace of X. And part A says that if R is considered as a subspace of S, then this is the same as considering R as a subspace of X. So for these types of nested subsets, it doesn't matter whether you think of the subset as being a subspace of an intermediate set or of the larger set. Next, part B concerns bases for the subspace topology. So if B is a basis for the larger space X, then this new set, BS, which is all the intersections of basis elements with S, this collection is then a basis for the subspace topology on S. So if you have a basis for the larger space, you can obtain a basis for the subspace by just intersecting all basis elements with S. The next part concerns limits of sequences. So if we have some sequence, Pi, which lies in S, and there's also a point P which lies in S, then the sequence Pi converges to P in S if and only if the sequence Pi converges to P in the larger space X. So part C is saying that for a sequence, it doesn't matter whether you think about the sequence as lying in the subspace or whether you think about it lying in the larger space, convergence will be the same in both cases. The final part, D, of this proposition says that subspaces inherit some nice properties from the larger space. In particular, if the larger space is Hausdorff, then also the subspace will be Hausdorff. If the larger space is first countable, then the subspace will be first countable. And finally, if the larger space is second countable, then also the subspace will be second countable. The proof for all these items is pretty straightforward. Mostly it just boils down to checking the definitions that are invoked in each case. So I won't be doing that here. However, these are some points which are good to keep in mind when one is working with subspaces. And mostly these points are just saying that one doesn't need to really worry about transitioning from a larger space to a subspace most of what one is interested in is preserved in the process. That wraps up what I wanted to say about subspaces. In the next video, we'll be looking at product spaces, which is another way to construct new topological spaces from existing ones.